So today we're going to sort of have an introduction to MPI and randomized algorithms as well. The second assignment should be, or assignment number 1, will be up later today, and we'll go through some of those issues related to that as well today. So very quick recap of last time. We sort of looked into some more parallel algorithms, specifically parallel search and parallel sorting, and we considered both merge sort and sample sort. That's basically going to be one of the problems for your next assignment, is to implement sample sort. I'm going to give a very quick overview of the problems here, but it's going to be a little bit, there are going to be multiple steps, and this time I want you to submit a report as well. So it's going to be, think of it as a part written assignment, part programming. Some of the answers will require you to implement these algorithms. What are we going to talk about today? I'm going to talk about network topology. So far when we have considered algorithms, we've been looking only at the algorithmic aspect. We've sort of ignored communication. We've looked at from sort of the algorithmic structure, how we can estimate the complexity. And so most of what we've looked at so far considers only the problem size and what the depth or the dependencies within the program structure are. Today we're going to look at network topology. And here again, in many of the cases when you are implementing these on machines, you might not directly be aware of the topology. The topology is how the network is connected together so that you can figure it out. But again, similar to how we use the work depth model as a tool to help us better understand the algorithms, this is another way in which you would both analyze the algorithms and potentially even help it to guide your implementations. So we're also going to talk about communication primitives. This would, think of it almost as a very quick introduction into MPI. What is the general model? What is sort of the minimum set of communication primitives that MPI exposes to you so that you can design and implement your parallel algorithms. You'll get a quick taste of randomized algorithms. This is not a full introduction into it, but we talked about this, that divide and conquer is one strategy and randomization is another strategy. During this course, we will at other times get into it, but I'm going to give you a very quick introduction into both randomized algorithms and graph algorithms using graph coloring as an example. This is one of the simplest versions of a coloring of a randomized algorithm that you would have, and this is one of the there's a second problem that you guys will be asked to implement for your next assignment. So let's look at the network model. And this is sort of kind of specific to message passing model. So for now, ignore your shared memory models. We are considering an interconnect where different processes are communicating with each other by sending messages back and forth. Okay? You could have this also implemented within a shared memory machine where they are communicating not directly via shared memory but are using messages to communicate instead. And that's becoming fairly common as well. The big assumption that we make here is that the memory is distributed, which means that one process cannot directly access the memory of another process. We generally like to think of the network in terms of a graph. We're going to look at graph problems later. It's the same idea here, that the whole machine is basically a graph made up of nodes, which are the processors, and the edges of this graph correspond to the communication link. And it's a two-way communication link. It's not a one-way communication link. And one way to look at it is, again, if you extend the graph paradigm out here, is that the weights of these edges are sort of going to be indicative of the communication bandwidth that you have available between these two nodes. So most of this is how we're going to look at it. In most cases, we would like to think of these as being asynchronous. Now, this is something that you should get familiar with. When you look at different systems, and we will actually later on in the course look at some implications specific to Hadoop and how Google has gone around circumventing this or working within this with some of their recent work. But it's important when you consider a large parallel machine of any sort, and they're all independent of each other, what does it mean to be synchronous or asynchronous? Because if you design a system, so if you go back to what we talked about with the von Neumann model, everything forces it to be synchronous, that there is a clock at every time, every tick we are doing a particular operation. When you're in parallel, you want to think whether there is some sort of a synchronization between these machines or not. Now, when we look at some of these algorithms, you will realize that some algorithms might require you to be synchronous, even though fundamentally the machines are going to be asynchronous. Especially in MPI, this is true. The clocks are not really synchronized. They are happening independently. So you need additional constructs to enforce some sort of a synchronization between it, your different programs.
In synchronous, when you say synchronous, you're meaning like when you're saying when machine instructions are going in.
Not necessarily. It doesn't have to be. So think of this as more of an abstract notion. You can think of it in terms of when you consider a particular programming model and saying that things are going to happen in a particular sequence. I mean, at each processor level, there's still a sequential order. Can you make an assumption that these operations are synchronized across the machines explicitly, or whether it's something that you have to?
Okay.
Given the nature of the machines and given the nature that this is completely distributed, especially when you go to large scale. Now, when you have, let's say if you have 4 machines connected together with a network, you can actually you can develop a programming model which is assuming that it's synchronized, which means that there might be a process in the background which is continuously synchronizing their time clocks, and then your programming model follows that clock with an implicit assumption that if I have reached at this point of the program at this time juncture, another process as well has. When you think of really large scale problems, you have to think asynchronous. You have to think with the perspective, and this is where we are going today with MPI, where this is sort of fundamentally the model that you have a bunch of it. It's like all of you are processors and you're all independently doing your tasks. And I'm not there to synchronize or to coordinate things between you. And so that's fundamentally asynchronous because different processes are going to be independent of each other, not really checking to see if somebody else is up. Sometimes you have to do it, and we'll talk about that as well. Fundamentally, there are 2 basic communication constructs. Send data to a particular processor and receive data from a particular processor. This is going to be the tricky part of it. There are one-sided communications. I'm going to skip that for now. But fundamentally, if I'm sending something to you, you need to be ready to receive it. Okay? Which means that as you program it, you're going to have to set up, yes?
Why there's a receive function?
Sorry?
Why there's a receive function?
Go back, what do you mean by why there is a receive function?
The processor doesn't know that it's going to receive this particular data from this particular processor.
This is you programming will have to take care of this. The thing is that fundamentally think a little bit more low level now. If you're talking of network communication, and I'm sending data from one machine to another, somebody has to be sitting there listening at the port or wherever I'm going. So you need to have explicitly. It's way too expensive. So you do have, so MPI and many other constructs will set up one-sided communication, which means that you can have a listener listening all the time for data coming in, but that's inefficient. So especially when you have control over your algorithm and you know how they are going to behave, and we'll take a look at some examples and become clear why they are. And it's not that you're going to be using only send and receive all the time. There are sort of higher level primitives which you would use to communicate across. You need to think algorithmically here, but fundamentally, all of them translate down to things like send and receive. This would be also similar to, so that is a scan primitive, for example, the prefix sum that we did, yes?
So the receive function in this case basically is some kind of a reset.
Fundamentally, yes. You have to realize that it's implemented differently, and it's implemented differently on different systems. What you have, the MPI in this case, or most frameworks as such, would give you something like this, which means that once you have a function of this sort, it is going to listen at some particular address, which is decided by whatever framework you have underneath. And it's going to expect a message from this particular processor J. which at that point should have sent. If your code is faulty and you're either sending when nobody's receiving or you're receiving when nobody's sending, then you're basically going to freeze up at some point. Okay? But whatever system you use, at the base level, this is what is happening. They have to communicate, and this is how you do it, and they are separate. Now you can have blocking and non-blocking versions of this, and those are detailed, but fundamentally, it's point-to-point communication at the end of it. Whatever you have built up, and most frameworks will have higher level communication, whether you're broadcasting, you're gathering stuff, you're doing reductions. This is what is happening internally.
Yeah, no, I agree that there's like, if someone sends, someone has to receive, like, it's surprising that you have from processor J.
As opposed to?
As opposed to, for example, you can have processes, right, that you do something, and at some point.
And you have a single listener.
Yeah, no, we have multiple processors that are listening, but the thing is, you just want to send it to the processor J. Maybe this is determined at the runtime.
It is determined at runtime. This is all of this is.
Okay, so this is.
No, this is a function call. This is what your code is going to look like, in a very simplified sense.
But your communications are still the way they are structured during the programs, right?
Yes. Yeah, but your I and J's are these are not static compile time definitions that I need to send it to this one. Everything is dynamic here, so it doesn't. I mean,
Okay, so the sender can return in the J.
your algorithm, your specific implementation is going to do it. And so, for example, some of the cases we considered, like in merge sort, when you're traversing a tree, and I think I had the discussion of where you would figure out whom to send to by just looking at the most significant bit or the particular order bit. So that's how you would decide whom to send to. And this is the structure that you define within your code.
Also, if you're receiving from different people, it's like that's the only way you can identify.
Yes. Now this is you're going. Let me get to it, because fundamentally that is almost that's lower level than what you want to really consider, and that's why you have APIs which are insulating you to some extent from the fact of which machines are exactly in this and what is their IP address and how should I actually send a low level message. You can implement it this way, but when we think at a slightly higher level of abstraction, now if you go about implementing a framework of this sort, so let's say you're not happy with MPI, you're not happy with Hadoop, and you want to implement it, you are probably going to say that these are the set of functionalities that I want my users, my API to define, and this is how I will implement it. Okay? And we're talking about MPI, and keep in mind that MPI is not like a single library that is available. You have different versions available out there. It's an API that defines that all implementations will follow these basic functions. They might have some peculiarities of their own. And when you get to large-scale machines, this is not true for CHPC. And you remember Anita mentioned that during the presentation last time that they're using MWAPITch, which is a particular implementation of MPI. If you go to large-scale systems built by Cray, the kind of things that you'll find in your national labs and built by IBM, they all have custom implementations. And these implementations run only, and they're tweaked and tailored for that particular machine and the kind of network that they have. So separate the two things. We are still talking at the API level that this is the kind of functionality that we would like to have. So why is it important? So let's consider some topologies. Now, if you have a bunch of machines, a very trivial way of connecting them together is sort of a linear array. You have a line. They're all connected to each other. You could also have a ring, which means that the ends are connected together. What that gives us is an idea of how long or what kind of latencies and bandwidth to expect as I try to send data from one machine to another. More realistically, you might have something like a mesh. Now, if you consider real-world like problems, you can map your problems down to some. Let's say you're doing image processing. You have a really large image. You're working for Google Maps, and you want to do a lot of processing. It makes sense to have a network topology like this because you can take a big chunk of localized data. It's 2D fundamentally, and you can map it onto each machine. And then you have a control over that. The probability that I'm communicating mostly with my adjacent neighbors is maximum, and they are close by, which means that my latencies, as well as the probability that somebody else is choking my network connection between these particular two processors is lower. And the chance that you would really need to communicate some data from here to here is much, much lower. So that's why it's important to consider topology. Again, given a mesh structure, you would also have the option of having a wraparound. The link between this is assumed to have basically one per task pair, so any given nodes we consider that is there. It's bidirectional. And I'll get a little bit more into this in a minute, but basically the time to send or to receive is basically going to be some combination of latency to start the communication and message or bandwidth. Yes?
Just to be clear, that this image represent, does the address image represent how that you can communicate on the packet computers, or that you can communicate with others with the latency?
Everything, yeah, exactly. So this is how you fundamentally you're going to have, you'll have to route your message through. Whereas for those who are sort of connected directly to me, both the latency and the number of hops that it takes, because your latency is going to add up every time you have to hop and somebody has to route it through. So just wait a minute, we'll get a little bit more into details and you'll realize this. One of the most common case, the structure that we will use fundamentally because of our algorithms, the way the algorithms are, and what the fact that you can take other topologies, things like a mesh or even a 3D mesh, for example, if you're doing a 3D processing, then maybe a 3D mesh is better, and you can embed them, is a topology known as hypercube. How many know what a hypercube is? Yeah, exactly. It's just a higher dimension.
For log tree, like if I have to go from 0, 0, 0 to the other side is 1, 1, 1.
Yeah. So you're basically flipping one bit at a time. So it's the depth. So that's what you're doing.
That makes sense, yeah.
You know that I can go to anybody different from so the maximum you would
Maximum
different.
is okay.
So you're just flipping one bit at a time, and there are multiple paths. So that is going to depend on your algorithm. So that's the choice you're making. So one thing I should also tell you is that as you go larger and larger, this is probably what you're going to be seeing in most large-scale clusters, which is known as a fat tree, which is basically that you build them up as a tree, and then you start having higher bandwidths across as you grow up, because so these are going to be connected with a lower bandwidth interconnect, and as you grow higher, there are more and more channels, so they can. It's also become, our largest clusters have become large enough that this is not exactly fully subscribed, which means that this connect is not necessarily twice as large as this, and 4 times and 8 times. They typically end up being oversubscribed, which means that usually
A little bit more than what?
no, a little bit less for economic reasons. It just gets too expensive. So you're scaling up very high, and you're basically making a calculated bet that not everybody is communicating with everybody at the same time. If you had an ideal fat tree, you would have it's equal to saying that this connection exists from here to anybody else. That level of bandwidth guarantee is there. But you try to make a compensation and you do it.
Is fat tree, can I see fat tree as a hypercube?
An ideal one, yes.
But
Although the hops are there, so it's a little bit trickier because
the
there.
hops, if what you're saying is if I implement it theoretically, then I can go from one link to other without compromising on my bandwidth. Even it won't even be log P. I can actually go in one. It will
Not necessarily. So you get a guarantee on the bandwidth.
Okay, but
You do not get the so there anybody who's one bit off is actually one link away.
Yes.
Not here. You might, so let's say that this one and this one being sort of one bit away, you would still have to go through the tree. So, but this is how practically a lot of them would end up being implemented. So the basic concepts, this is not the scope of the class, but fundamentally the issue is the fact that you have to route your messages through. This is what your framework does for you. You don't have to do it yourself. We are interested in some way of estimating what it is. Let's say that you work for a company and you want to build your own custom cluster for a specific application. You might have to make choices on what kind of a network topology am I actually going to incorporate. So it's useful to think of some numbers in terms of what it is. So you basically have to think in terms of the diameter. We talked about this. What's the maximum distance between any two nodes? Because that is going to dictate. The communication cost is basically latency, which is the time to initiate the communication. So adding your headers setting it up, reserving, opening a socket, and all the low-level infrastructure that you have to do. That's the latency that you have to do for every single message. And then the bandwidth or the channel capacity, which is usually going to be measured in terms of how much data can I send per unit of time. Both the number and the size of messages matters. And there is going to be a variability depending on how you implement it. If you're sending a lot of small messages, potentially you're not going to get the full use of your bandwidth. And this is sort of known from how you're going to set it up. So you might have to sort of pack your data, streamline it some way to get the full benefit that you have. MPI especially implements both of these, so you have the option of doing point-to-point as well as collective communication. Now, collective communication is where everybody is involved, or typically a chunk of processors are collectively doing something. Things like doing the reduction, things like doing a scan. We'll go through some of these. These are one way to enforce synchronization. Okay? And you also have these all-to-all messages where everybody is communicating to everybody else. This is for ease of programming, and sometimes you have no choice but to avoid collective communication. But fundamentally, you need to think of, sort of understand that these are bad. For the reason I talked about earlier, at the moment you force in synchronization, you are reducing the total amount of parallelism in practical systems. You want to avoid that. At the same time, if you have to implement something like a reduction, if you have no choice but to do a scan, you are better off using the inbuilt versions rather than trying to implement it using point-to-point communications yourself.
What do you mean?
So you can, right? So we talked about scans, so you can code up. So you can code up a collective operation by implementing the entire logic together. And there might be cases where you have to do it. But in most cases, if all you're doing is just the basic collector, then go ahead and use the inbuilt collector. Try to avoid it. So the reason why you might want to do is that you want to do something which is very similar to a scan, but you want to do a little bit of extra communication, extra computations interleaved with that scan. Maybe you want to implement it yourself. Right? So you have to sort of take it as a trade-off. Fundamentally, the inbuilt collectives are tweaked and optimized for many factors, including the kind of architecture, the kind of network, and everything. So if there is a choice, you should use it. I mentioned this earlier. Basically, the network model allows us both in terms of for thinking and measuring the communication cost and non-locality. So we think about how does data move between our nodes and what is the cost of moving data from one node to another. And so it sort of helps you analyze that. I've sort of clubbed both the size, it's the number of bytes, let's say, of your message. So it's the number, so you're going to have some data type and some size of the message, right?
So you're multiplying the forward transfer time at the end, so just the number of words in our message.
So
Yes.
the inverse of bandwidth depends on how
It's the inverse of bandwidth, right? That's the total amount of time. So how many words can I send per unit time?
So
Right.
that needs to depend on the units you take for bandwidth as well.
So yeah, exactly. So it's basically how much, that's the channel capacity, how much data can I push through at any given time.
Why is there a class? Presumably the multiply
Between,
TS and TWM.
the latency is just setting up the communication. So you're going to do it once and then I'm pushing everything through the network, and there I'm limited only by the bandwidth.
So now per word transfer times contains now hop time.
We are sort of ignoring it in this case. Okay, the simplified model. It becomes a little bit complicated because you're spending too much time analyzing, because the per hop time is going to depend heavily on the network and your direct communication pattern. We are sort of simplifying it by avoiding that and saying that we are only looking at these two extremes. The hops come somewhere in between these two. Like I said, low latency, low, if you're doing a lot of synchronization, you're mostly bound by the latency, and that's why it's important to consider it. And at the other end, we're talking about bandwidth, because if you're exchanging a lot of data, there is a small set of algorithms which are going to be limited by the number of hops. If you're doing arbitrary communication, right, then the number of hops might matter, and how you've basically taken your problem and mapped it onto it. So arbitrary graph problems will get affected by the hop time because you're not exchanging a lot of data, but you're doing fairly non-localized communication. In those cases, you would have to, but for a large set of problems, you can ignore this. And that's why we are ignoring it for simplicity's sake.
So this is only within 2 nodes.
What do you mean?
In other words, this is communication time only within 2 nodes.
So the way we analyze this is that you want to now think, like I said, we've already assumed everybody is distributed. So if you guys are all processors, you need to worry about your cost. So this is at each process. Ideally, if everything has been parallelized well, this is the same for everybody else, right? So, and this is going to be different. So like, if you consider sorting, for example, it's going to be sensitive on the data distribution and how you started off with. But that's going too much into detail, so we're going to analyze algorithm assuming that you can draw some general conclusions about it. Okay? So this is how much am I sending and receiving each process. So yeah, so let's think about this. The connectivity is basically the number of links required to remove a node. The bisection is to break it into 2 halves. And these both basically think in terms of the divide and conquer kind of strategy. It gives you an idea of if you are actually there, then you want to have something with a large bisection width. And of course, the cost is important because you want to also factor in that ideally I can connect everybody to everybody, which is a clique like the one on the top right, but you don't want to do it because the cost is going to be very high. So this is a very simple thing. Let's consider somebody like a bunch of machines connected as a ring or as a clique, which is a fully connected ring. So what is the diameter for the 2 cases?
Ring it is n, with the connected it's 1.
No, the ring is n by 2 because you have anybody to anybody. If it was a linear array, it would be n.
I would communicate backwards.
Yes. So it's p by 2 in this case, and it's 1 obviously because everybody is connected to everybody. What about the connectivity?
2 versus 1. Sorry, 2 versus n.
N minus 1. Because each is connected to
Only n.
p minus 1, right? So this is important. This is somewhat academic in nature, but you want to consider these factors. And so if you have an arbitrary topology, you're constrained by something, you want to know what it is. The bisection width for the fully connected case. You should go home and try to work it out. It's p square by rho 4, which actually comes from the next part. It will be clear. What is the cost?
Here n links. N minus 1 links.
Yes. Here?
Here it is n minus 1 to the power n.
Yeah. So it's n minus 1 by 2. Because you don't have 2 connections. You're saying that I have a single connection between every pair, right? So this is basically what you're considering. So the cost is very, very high. Ideally, I would like to have something like this because all the other characteristics are super nice, but this is too cost prohibitive. So for a large network. We should also like to consider the hypercube because this is what we're going to be doing most of the time. And so when we consider many of our communication paradigms, we want to assign a cost to it, and so we're going to be considering the diameter, which is where the log p terms or the depth of the tree comes in, which is the distance. The connectivity is also log p, right? To remove anyone, you have to isolate him with every other process which is connected or different from him by a single bit. So that's also the depth, or again log p. The bisection width is p by 2. You have p, right? So you want to separate it out, and again, the factor of 2 coming from the fact that it's a shared link. The cost is basically p by 2 times the depth, right? So that's sort of giving you an idea of it. Keep these numbers in mind as you do your assignments and all. You might have to think about these things. It's not that important. Now, let's look at what you can do and why the topology might dictate the way you would do this. So let's consider an example problem, which is how do you perform a fully distributed matrix-matrix multiplication. So you have 2 matrices, A and B, right? And you want to do matrix multiplication. Everybody knows how to do matrix multiplication? Yeah. And for this reason, now let's say that we know this is the problem that I need to solve, and for that reason I'm going to choose a 2D grid topology. Okay? So we have a 2D grid. I want you to think both. Actually, let's stay. So this is easy because I have a matrix. I think I can take this. This is really large. It won't fit in single memory, and I want to map it onto my machines. And so this is what I need to compute: C, I, J, summation over K, A, I, K, B, K, J. Right? So how do you want to divide the data across the processors?
We can write it.
To each processor, you give a corresponding row and a corresponding column. So each processor will just do one of these CRJs.
So here's the problem, right? That is easy. It is easy, but it doesn't scale well. What is the level of parallelism that you can have? You're still limited.
By the size of the row.
Yes. So if that is very large, that's the number. So let's say everything is symmetric, everything is n by n times n by n. You're still, the number of processors, the maximum number of processors that you can have is going to be n.
Yeah, but the time is going to be high with the core square.
Yes. You want to think both ways. What if each row is so large it won't fit on a single memory, machine memory? Yes.
So do we divide the matrix into n by 4 into n by 4 matrices and give it to each processor? And we can multiply their own matrices and
So again, yes. So fundamentally, you want to think to the extreme. So I want to break it down to the level that one entry on each matrix sits on each processor, right? Worst case scenario. That is driving your level of parallelism to n squared, right? If I have an n by n matrix, I want to drive it down all the way to that level. Ideally, you won't, but you want to break it up into blocks because that's giving you the flexibility. And actually, if you think about it, the fastest, even a sequential or a vectorized algorithm, the way you would implement matrix multiplication would be to divide it into blocks. The complexity is actually lower than, because you reuse some of your calculations, than actually writing a simple triple loop to do this. So you can actually, you should, outside of the assignment, for those who are interested, try to implement matrix multiplication by writing just a ijk loop and computing Cij equal to the product of ik, bj, kj, versus using blocks where you're computing local blocks and then doing it. It's actually it's faster and lower complexity as well. So for both those reasons, we want to basically keep these in blocks. So A is basically mapped in the matrix fashion across all of these processors, and B is as well. And each process is individually going to compute Cij corresponding to its own block. Okay? It's not possible, it's only along the rows in the column, and that's what we are basically leveraging to get this. If you had a data dependency between this one and somewhere out here, then you have to come up with a different strategy, right? But this is fairly typical of a lot of things that you're going to be doing. A lot of algorithms that you encounter in big data end up being large matrix operations. So this is something that you can do. And mapping a 2D mesh structure, even a wraparound mesh, is actually not hard and is a reasonably good model for most modern clusters. So it's not a complicated algorithm, yes?
Basically, this is row by column multiplication, but with the difference of row, the cells of rows, columns are columns.
What do you mean?
It's basically row by column multiplication.
I mean, that's how you would do, that's your definition of your basic matrix.
Except that cells of rows and columns are coming in stream.
They are coming in streams, so you can think of it as coming into, but you never have one entire row or one entire column in memory. So this scales to that particular situation. So if you consider the distributed framework, the way you would do it is that each of these processors are going to read from their local disks, right, or wherever you have. You're going to stream in only that particular chunk, and then everything else is exchanged between the network, and then eventually it's written. So it's basically efficient in terms of how much you read in, how much you need to store, and it scales perfectly to whatever size you have, whether you have limitations on your I/O or you have limitations on the amount of memory that you have available. So that's why it is. It allows you to use the right partitioning. keep in mind also that if you go for a row or a column kind of thing, eventually you're talking of a fundamental operation here, which is matrix multiplication. That's not probably going to be where you're going to stop. At some level, you want to be eventually, you're hopefully doing something with Cij that you're left with. So if you did it the other way around and then you have to move too much data around, then you are inefficient for the subsequent stages. So many times, even if you are saying that I can potentially fit everything into memory, possibly what you want to do in the next time step is going to be limited by that. So you want to be able to parallelize to the fullest extent at each step of the way, rather than have to communicate. So, okay. So let's actually go quickly through. So this is, I expect all of you to go Google and look into MPI, but I'm going to go very, very quickly into collectives. So I talked about send and receive, but we have to think of collectives. This is what makes your job easier. Not everything can be easily implemented with send and receive without having to reinvent the wheel. So a fundamental concept, so how does MPI go about doing it? I mentioned this earlier that MPI does everything in a truly distributed sense. So there is no central coordinator of sort or a head node which is sort of effectively controlling the program flow. When you write your code, you're going to write it, it's the same piece of code which is going to get executed on every single node and every single process that you have, and everything else has to be managed internally. So you want to be able to, so let's say we're thinking about a divide and conquer strategy. You want to have collectives where you're talking or communicating with a subset of all processes that are active at that point. Okay? And this is handled in MPI. It's transparent to you by using what are known as communicators. So when you start off with all the processors in a communicator. And let's say you have some logic of dividing up your work. You can take this communicator and divide it into two parts, and they would individually communicate with each other. So the concept of a communicator is basically if you have a collective call, which processes are part of it. It's just basically, it's a set. It defines the set of active. And it's basically, so it determines the scope in which a point-to-point or a collective operation is to operate. They are dynamic. So this is, although we start off with what is known as MPI COM world, which is sort of the global, the size or the number of processors that you launched your job with, they are dynamic. You can create them and you can destroy them at will. Okay? This is always going to be available for the scope of your program, but fundamentally you can divide these up.
Is a barrier something like everyone?
I'm not reached barrier yet. I'm still at communicator. I just want you to understand, because the communicator will show up. Every single function call is going to, you have to specify in which scope this collective. If you have to say that there is a reduction to be performed, you need to tell MPI that is this reduction going to happen in the scope of all the processes or only a subset? And you might have to do it. So especially when you implement, you might not actually come across this. You can. It depends on how you go about implementing it for this assignment. But especially if you think of implementing something like merge sort, where you're basically dividing up the work at every step. A straightforward way to do this would be to use communicators. You split it up, create two communicators, and go on till you have exactly one process in each communicator, at which point you do a local sort and start merging as you move up the tree again back to the original communicator. So that would be one way of doing it. So the simplest thing that you would want to use, assuming that all you care about is just synchronizing all my processes at some point and not really exchanging any data, you have a barrier. A barrier just enforces synchronization. Okay? It only uses a single argument, which is the communicator, which is that which set of processes do you want to synchronize at that point. So at some part of your code, you drop in MPI barrier. Every single process which is part of that communicator is going to wait until everybody has reached. So you just basically set up a blockade till everybody marches up to that point, everybody is there, then you can move on. This is something that you should avoid. It's a very, very bad idea for large scale. But it's a very useful tool for debugging. So if you're not sure, if something is not working, then you can at least say that I want to figure out, because keep in mind that unlike sequential, different processes are doing different things at different points. So you don't know where something has gone wrong. So this is a good way to isolate it. So when you first start doing it, writing your initial programs, set up a lot of barriers which you can eventually remove. This is just to make sure that then you are enforcing synchronization across all of these processes, and then eventually you can remove it. It's really bad for performance, okay? Because one process might be faster in one part, and if you enforce a barrier, you're going to be only as fast as the slowest process. Whereas, at least in an amortized sense, you might, if you let the program run through till the end without having any barriers, there is a chance for other processes to catch up or slow down one way or the other. So it's ideal if you can avoid it, use it for debugging. Now, this is the most interesting part, right? Well, almost. This which is data movement. So I'm going to be moving data back and forth. So how do we do it? We talked about send and receive, but a lot of times that's not what you want to do. You want to be doing something more complicated. You don't want to be writing network level code that send data to this particular processor, right? So these are broadly the main functions which are there in MPI for exchanging data between processes within a communicator. They're broadcast, gather, scatter, all gather, and all to all. I'll talk about it. You see that all of these have a V variation. V is for variable size. By default, the non-V versions assume that everybody is sending the same amount of data. Everybody is sending 1 integer, or everybody is sending 10 integers. So it's just easier, and you have efficient communication paradigms for when everybody is sending the same kind of data and the same amount of data. The V versions are very powerful. When you have real world problems, you probably are using the variable size versions. I'm going to go through this, but fundamentally there's nothing any different. It's just that you have extra arguments for how much each guy is sending, to whom. So the first is, of course, broadcast. It's very simple. That's sort of the signature. You have a buffer. This is just a C interface. There are other interfaces. You can use whichever one you want. You have the data. So think of a grid structure like this. Data is distributed out here, and here are your processors. Some particular processor, I'm referring it to as A0, but it doesn't have to be A0. Some processor in your collective has this data, and you want everybody to have a copy of this. Okay? So this is a broadcast. I have some data. I want everybody else to have it. Okay? So this is sort of before and after. Is this clear? So in terms of the algorithms that we talked about, where are we thinking of a broadcast? The ones that we have covered so far. Did you encounter a case where we might have to do a broadcast? So in sample sort, you collect the samples onto one processor, does the local sorting, figures out the bucket.
After figuring out
The buckets. Yes. So once you have figured it out, it's only one. So maybe in your algorithm, you have a part where you think that it's too difficult or it's not worth it to do it in parallel. You might just want to get that information onto a single machine, do it quickly and efficiently, and then send it back to everybody that, okay, now let's do it in parallel again. This is the sequential part of your code, right? So there you want to broadcast. Okay? Gather and scatter. These are very useful tools that you are going to have. Gather basically takes data from all processors and brings it to one. Okay? Again, going back to the sample sort example, everybody has their splitters. They have locally looked at their distributions and they have picked out their samples. You want to gather them on a given machine. Who's going to do the local sorting? So that is gather. So you have all processes and you have some data set spread across. You get them onto a single machine to do your operation. The scatter is the exact opposite. I've done something on each machine. Unlike a broadcast, the kind of information I need to send to every processor is different, which means that I'll have an array of size, the number of processors, where I have values for each of them. And then I call a scatter function that's going to take this and let everybody else know what their values are. Okay? So gathering information, scattering information. Okay?
can I send?
So that was scatter and gather. So you also have the all gather function, which is basically taking data which is distributed across all your processors and making sure that everybody has a copy of this. So this is everybody is gathering this information. What I'm saying, you need to understand is that MPI is basically giving you very efficient implementations for doing this in the right way, so that you don't have to worry about it.
And in some sense, let's say.
This is basically a gather and then a scatter.
And like in some sense, Kingspeak would have its own implementation of MPI all gather for its hardcore process.
Not Kingspeak, but
In some sense.
more expensive machines. Yes.
Okay.
So there are like some of the IBM Blue Jeans have super efficient implementations of all gather.
Okay.
So literally order one for all practical purposes. Okay, so they have hardware support. They tweak. So if one of the let's say for one of the nuclear simulations, you say that no, I have crappy code and I don't want to redesign my algorithm and I have lots of all gather in my code, you won't tell IBM that please, we'll pay you this much money, design it. So the network, the hardware, the way it's routed, everything is super efficient so that this is tweaked to the head. And that's basically the advantage of having an API of this sort, that if you have a dedicated system, you can say that, no, I'm only going to deal with large machines, small, medium-sized machines, and I'm going to have a dedicated interconnect where everybody is directly connected to everybody else. And then it'll hold true. And so you're not paying a cost for doing broadcasts and all gathers and so on any more than you would if you had a super efficient algorithm and an implementation. So is it clear what all gather does? It's the same as doing a gather and then doing a scatter, right? So, sorry, doing a gather and then doing a broadcast, not a scatter. Clear? The final one is all-to-all. This is sort of the most powerful, and you will be tempted to use it quite often, which is everybody is sending data to everybody else, right? Which is, and whether you like it or not, when you're doing heavy data processing, this is something which ends up happening quite often. Where have we seen this? In the algorithms that we covered.
When we sorted the stuff, we had.
This is the last stage, or the second last stage of sample sort.
Yeah.
Once you've figured out what the buckets are, once you've figured out which data needs to end up where, everybody just bins his own data, and I send it to everybody. So everybody is involved in communication all the time. And so that's what you're doing. So everybody has some data, everybody has a piece that needs to end up on some other processor, and you're probably receiving from everybody. Keep in mind that given your data distribution, so the more powerful version of this is the all-to-all V, which is the variable version. You're sending different amounts of data to different processors, some of which might be zero, right? But then in one function, basically you have exchanged all your data, and so parallel programs written with all-to-all V, or at least if you can break it down, is going to mostly look like sequential, all-to-all V, sequential, and done. Because you just had these few points where you had to exchange data from across all processors and done. So these are the ways you would move data around. But there are slightly better functions, higher level functions, let's say, which actually compute on the network. So they're computing, and it's truly elegant if you think about it, that as you're moving data around, as you're moving data through the network, you're actually doing computations on them, and you're getting. Reduce is very popular, everybody knows MapReduce, but you need to understand what it really does, and we talked about this. The other is the scan that we've already covered, the prefix sum. MPI natively supports both of these. Again, they have efficient implementations, so if you need to use them, to use the functions. So they're going to be significantly better than what you're going to be able to implement. I'm not saying this, but in general. When we look at reduction, there are three varieties of reduction available to you. There's the standard reduction, and I can go through the arguments. I should probably choose a different color next time. So you have the data that you're in your send buffer, you have a receive buffer where you're going to receive the result. It's a reduction, so only one processor is receiving it, keep that in mind. You have the number of data, so you could have an array of 10 elements or a single element or whatever else you have. It's going to reduce all of them together. The data type. What is the operation? So the reduction is not going to be limited to only an addition. If you wanted to, let's say, do a sum of all the numbers. So everybody has an integer or a double, and you want to compute the sum, right, at some location. Maybe you're implementing conjugate gradients, and you want to do a reduction on the norm to figure out what the next direction should, or the scaling for the next direction should be. But you can do a max, you can do a product, you can do any operation. And I'll probably try and come up with a good assignment for you guys, but you can decide and you can design your own operation to do as well. So let's say that you're moving data around and you want to do some very special, funky computation. You can actually define your own operation that is going to be used across all of these, and I don't know what happened to my laptop. The other option, which is the other one, of course, it's the scan. I'm not calling it a prefix sum because in MPI it's a prefix operation. Again, you can do a prefix sum with a product, you can do a prefix sum with a max. So maybe think of things like max and min of values spread across. You have to do some samples, if you have to intelligently pick values from different processors. These operations become important and you want to do it in a prefix fashion. Yes?
It can be any operation in the source.
Yes. So that's what. Sorry, I said that's why I'm not saying it's a sum. So you have. So MPI defines a bunch of standard operations. So you can do those, and you can have your own custom operations if you want. Let's say you have some funky bitwise operation that you want to compute. You can actually use that, and at each point, as the data is being gathered together to do the reduction, it will, or the scan, it's going to apply that operator. And it's actually a very powerful tool if you use it properly, because the underlying implementation is very efficient, and you have the option of specifying your own operator for that. Okay, we are actually almost done with time, and we haven't even gotten to coloring yet. But anyway, so let's look at assignment problem 1. I'll adjust the dates accordingly for the submission due, but let's consider this as an example of what we've just talked about. I kind of hinted at some of these issues as well. The first problem that you're going to implement is sample sort in parallel. This is the easiest version, so the text, the official text for the assignment is going to have a little bit more details and variations that I want to do. But just to give you an idea of what it requires, this is how you would do something like this. You're going to do a local sort on each process, so that's going to be the same code running on every single machine. So do a local sort, and you pick samples, so you can go about figuring out what samples to pick. I'm going to gather these samples at root, right? Now, root is a sort of a weird term. It just comes from the early implementation. It's processor 0. It doesn't have to be processor 0. It's any processor. You can randomly pick a process. It doesn't matter because everybody is equal. And that's sort of a bottleneck as well, so you might want to think about how to avoid that. You locally sort, only the root does this. So you would have some code which looks like, if I'm root, sort my samples, because the others don't need to do anything. They don't have the data to do anything anyway. You sort the samples and you pick the splitters, right? These are basically your buckets. Those are now broadcast to everybody else, right? Once everybody receives the range for each of the buckets, you're going to take a look at your own local data and you're going to bin them into these buckets. Binning in this sense is basically going to tell you you're going to create the map that I need for my all-to-all, right? The all-to-all requires you to send data from one process to every other process. So when you're bucketing, you're basically saying that this data needs to end up there. That's what you're doing. Then you have a massive all-to-all V. It's an all-to-all V because the distribution is arbitrary. You don't know how many data, how many samples or how many data entries I need to send to a given processor. Once you have done this all-to-all, you receive data which corresponds to your bucket, your range. you do a final local sort. You can do a merge at this point if you want because they were initially locally sorted, but it's almost as fast or even faster to do a sort at this point and you're done. Is it kind of clear how you sort of go about writing something in parallel using these building blocks? Okay. Let me